time to start to take a closer look at covalent bonding. And so here we have our typical depiction of a two-atom system, one nucleus, the other nucleus, and thinking of the electrons in terms of particles, those shared electrons being attracted to both nuclei. And notice that this picture also goes into the repulsion that exists there, and that is significant. Down at the bottom of the picture, we have the electron cloud idea, so we're thinking more in terms of electron density. And so notice that we have increased electron density between the two nuclei, which is a bonding situation. To understand this better, let's take a look at this animation of the bond forming. And so in here we have the two atoms coming closer together, and what we're looking at is as the atoms come closer together, there's a minimizing of energy. So as those 1s orbitals and the hydrogen overlap, the energy becomes minimized. Now, if you try to keep putting them closer together, right, so those electrons are attracting, if they keep trying to get closer together, the repulsive forces that are in our picture here start to raise up that energy. So those repulsive forces, again, are going to make the energy go way up. So what they do is they basically try to balance that out, the stability that's gained from bringing the s orbitals together and the repulsive forces that are pushing them apart. And where they balance out is determines basically the bond distance, the distance between the two hydrogen nuclei. So in the case of hydrogen, it's 0.74 angstroms, the distance between the two nuclei. And again, you get an idea of the energy drop then too, this negative 436 kilojoules of energy per mole of molecules that form this. We're going to represent the covalent bonds using dot structures, similar to what we saw before, and similar to the ionic. Here we have a methane molecule. When we take a look at it, and again, this is just kind of an animated depiction of, we look at the hydrogen. Each hydrogen now has its kind of stable octet of electrons. And if we look at the nitrogen in the middle, right, it also has that stable octet of electrons. And we can do this for a number of different things. We've seen this before. We can do hydrogen. We can look at things with double bonds, for instance, oxygen. And of course, the next section we're going to do is more in depth on drawing these Lewis dot structures. So we would have oxygen there. We could do methane. And we're just showing using dots to represent those valence electrons that are going to be involved in the bonding. So these are several that we could take a look at. If we did one that's going to be useful to us in the next section, hydrogen to chlorine. That would be an interesting one also. Something, let's see, water. We get a dot structure, it looks something like this. Okay, etc. So we'll practice doing more of these, but so you get the idea that the dots are showing electrons that are being shared between the nuclei. Now, these shared pair of electrons are not always shared equally. If we have two of the same type of atom, or atoms from the same element, such as F2, fluorine, we have an equal sharing of the electrons. So the electron density that's between the two nuclei that's involved in this bonding is spread out evenly between the two. However, if we look at the HF bond, the shared pair of electrons there are not going to be shared equally. The fluorine actually is going to have a stronger pull on those shared pair of electrons. What this does is create a situation where you have an uneven distribution of charge within the molecule. So the picture down here has, to the left side, so if we bring this over for this HF, to the left side, which would be the hydrogen side, would have a positive charge. To the right we would have a negative charge, and the distance between those two center of charges we would call the radius. Now, how do we determine that distribution of charge? Well, we're going to look at the electronegativities. Now, these are very close to the, these can be explained, it's a periodic trend, so it can be explained using effective nuclear charge and how far the electrons are involved in bonding are away from the nucleus. In this case, we'd be looking at both atoms. But you can see that there's this trend. And in the last example, we had hydrogen and fluorine. So we have hydrogen with an electronegativity of 2.1 and fluorine with an electronegativity of 4.0. So we see there that the fluorine is going to have a much higher electronegativity than the hydrogen. So it's pulling stronger on that shared pair of electrons. What this creates then is what's called a dipole moment. So if we take a look at that molecule, again, I'm just going to use a dash now to represent that pair of dots. We would say that the electrons are pulled toward the fluorine, making that side partially negative and the other side partially positive. We could do this for any other combination or any other bonding situations. So if we did the one in the first case with nitrogen and hydrogen, again, let me put dashes in here for these instead of dots. If we go back to our table of electronegativities, we see nitrogen is 2.0, hydrogen 2.1. So when we look at the molecule here, we have electron density pulled toward the nitrogen in each of those bonds. So that's going to make the nitrogen have an accumulation of negative charge, and the hydrogen would have positive charges. So all of these are both examples then of bonds that have dipole moments to them. And we'll get into the dipole moment of an overall molecule after we talk about the structure of these things. We need to do a little bit with VSEPR first. If we take a look at these these four depictions, we have HF, HCl, HBr, and HI. And so notice that we have a much bigger color gradient difference with the HF than we do as we progress on to HI. Now, so the reason for that, if we look back at our table of electronegativities, what happens to the electronegativity? Well, as we go from fluorine to chlorine to bromine to iodine, by the time we get to iodine, there's not much difference in electronegativity between the iodine and the hydrogen. So when we look at this, we have a 0.4 difference in electronegativity. We also have a much bigger bond length with that one. So our dipole moment then becomes much smaller as we get larger. This is going to have an implication when we start talking about intermolecular forces, boiling points, vaporization, heats of vaporization, those types of things. So our next step is going to be to take a look at how do we come up with the structure for these. So we're going to have to start with the Lewis dot diagrams. You'll see that those are going to get a little bit more complicated this year. We're going to want to kind of incorporate or increase our sophistication on those.